On a clear winter night, if you step outside and look toward the constellation Orion, something faint catches the eye just below the hunter's belt. It appears as a soft smudge of light, barely there, like a fingerprint left gently on the darkness of the sky above. This is the Orion Nebula, one of the most beautiful structures in our entire galaxy, and one of the closest stellar nurseries to Earth. Even from a distance of roughly 1,350 light-years, it offers itself to anyone patient enough to look upward on a cold evening. I remember the first time I truly noticed it, standing in a quiet field far from city lights, my breath visible in the winter air. At first I thought it was just another star, a bit fuzzy perhaps, softened by the atmosphere, or by my own tired eyes after a long day. But the longer I looked, the more it seemed different from the sharp points of light surrounding it, as if it held something more within its gentle glow. That faint smudge, I would later learn, contains enough material to build thousands of stars, all slowly taking shape over timescales beyond human comprehension. Through a small telescope, the nebula transforms into something far more complex and beautiful than that first glimpse might suggest from naked eye observation alone. Wisps of glowing gas appear in soft pinks and subtle blues, curling around darker regions where dust blocks the light from behind. At the heart of the nebula, 4 bright young stars sit close together, their combined light illuminating the gas that surrounds them like a lantern. These 4 stars are known as the trapezium, and they are among the youngest stars visible from Earth, only about 1 million years old. 1 million years sounds ancient by any human measure, yet in the life of a star, it represents the very first chapter of existence. Our own sun, by comparison, has been shining for nearly 5 billion years, and has billions more ahead before its fuel runs low. The trapezium stars are newborns, still surrounded by the gas and dust from which they formed, still shaping the nebula around them with their light. They are so young that if the entire history of the sun were compressed into a single year, these stars would have been born less than 2 hours ago. You're listening to the Drowsy Astronaut, and tonight we're taking a slow, unhurried journey through some of the most beautiful places in our galaxy. These are the stellar nurseries, the great clouds of gas and dust, where new stars are quietly coming into existence, one patient step at a time over millions of years. There's no rush here, no urgency, just a gentle unfolding of cosmic creation happening right now across the night sky above us. If you'd like to mention where you're listening from tonight, or what the sky looks like where you are, the comments are always open. And if calm explorations help you unwind, a like or a subscription helps others find these slow journeys through the cosmos. For now, let's just settle in and return to Orion, where something remarkable has been happening for a very long time, waiting for anyone who cares to notice. The Orion Nebula stretches roughly 24 light-years from one side to the other, a distance so vast that light itself takes over 2 decades to cross it. To put this another way, if you could travel at the speed of a passenger jet, crossing the nebula would take about 30 million years of continuous flight. And yet, from our vantage point on Earth, this immense structure appears small enough to cover with the tip of your little finger held at arm's length. The universe is generous with such quiet contradictions, offering grandeur wrapped in the appearance of something small and soft and easily missed. Within this vast cloud, roughly 700 new stars are in various stages of formation, some barely more than dense knots of collapsing gas. Others have already begun to glow with their own light, though they remain hidden behind thick veils of dust that ordinary telescopes cannot pierce. The process of star formation is wonderfully slow, unfolding over timescales that make human history seem like the blink of an eye in comparison to such cosmic patience. A star that begins forming today will not shine fully for another 100,000 years, perhaps longer, each step gradual and unhurried, beyond all human experience of time. The gas in the Orion Nebula is mostly hydrogen, the simplest and most abundant element in the entire universe, the raw material from which stars are made. This hydrogen glows with a characteristic reddish-pink color when energized by the ultraviolet light pouring out from the hot young stars at the nebula's center. The blue tints visible in some images come from light reflecting off tiny dust grains scattered like sunlight through a hazy afternoon sky on Earth in summer. Together, these colors create the soft, painterly appearance that has made Orion one of the most photographed objects in the night sky for well over a century now. Astronomers have been observing the Orion Nebula since at least the early 1600s, when telescopes first revealed that the fuzzy patch was more than a star. Over the centuries, each improvement in telescope technology has revealed new details, new structures, new reasons for wonder and quiet appreciation of this cosmic nursery. The Hubble Space Telescope captured images of such clarity that individual protoplanetary disks became visible, flat rings of dust surrounding young stars where planets might one day form. More recently, the James Webb Space Telescope turned its infrared eyes toward Orion, peering through the dust to reveal hundreds of objects previously hidden from human sight. What these observations have shown is a place of ongoing, patient creativity, where the raw materials of the universe are slowly being transformed into something entirely new. The gas does not hurry, and the dust does not rush, and gravity does its gentle work over timescales that dwarf even the longest-lived civilizations imaginable on any world. There is something peaceful in this slowness, something reassuring about a universe that takes its time with such important work as making stars. The Orion Nebula has been doing this for millions of years already, and it will continue for millions more, whether anyone watches or not. The nebula is part of a much larger structure called the Orion Molecular Cloud Complex, a vast region of gas and dust spanning hundreds of light years. Within this complex, the Orion Nebula is simply the brightest and most visible portion, the part closest to us and most directly illuminated by the young stars inside. Other regions of the complex remain dark and cold, not yet stirred into star formation, patiently waiting for their turn to begin creating something new. These dark regions are just as real as the glowing parts, just as full of potential, simply quieter and less visible for now to our instruments. Standing outside on a winter night, looking up at that faint smudge below Orion's belt, it's possible to feel a gentle connection to something vast and ongoing. The light reaching your eyes tonight left the nebula over 13 centuries ago, traveling through the emptiness of interstellar space to arrive precisely at this moment. In a sense, you are seeing the past, a message from an earlier time, delivered at the speed of light across an unimaginable distance. And yet the nebula continues its work right now, in the present, building new stars that will shine for billions of years into a future we cannot imagine. The colors you see in photographs are real, though sometimes translated into wavelengths our eyes can perceive more easily, from the original infrared or ultraviolet. The shapes are real, the gas is real, the dust is real, and the slow, patient work of gravity pulling matter together is happening continuously, every moment. Nothing in these images is invented or imagined, only revealed by instruments more sensitive than human eyes, shared with us as a gift from science. The universe really does contain places this beautiful, this vast, this quietly creative, and the Orion Nebula is simply one of the closest examples to home. As the night deepens and Orion wheels slowly across the sky, carried by Earth's rotation toward the western horizon, the nebula remains constant in its glow. It does not flicker or change noticeably on human timescales, even though profound transformations are underway within its depths every single moment. Stars are forming, gas is collapsing, dust is swirling, and light is traveling outward in all directions to illuminate the surrounding darkness of the cosmic neighborhood. All of this happens in silence, without urgency, without hurry, at a pace the universe has kept for nearly 14 billion years now. Perhaps there is comfort in knowing that such slow, beautiful work continues, regardless of anything happening here on Earth, in our lives or in our daily worries. The nebula does not know we exist, and it would continue its patient creation even if no one ever looked up to notice. But we do look up, and we have looked up for centuries, and each generation has found something new to appreciate in that soft glow below the hunter's belt. The Orion Nebula is our nearest window into the ongoing story of stellar birth, a story that connects us to the deepest workings of the cosmos. And yet, as beautiful as Orion is, it is only one chapter in a much larger story of stellar nurseries scattered throughout our galaxy and beyond. Some of these nurseries are far larger and more dramatic than Orion, containing enough material to birth not hundreds, but thousands of new stars. One of the most famous of these structures has been captured in an image so iconic that it changed how many people think about space and cosmic beauty. That structure rises in columns of gas and dust, illuminated against a glowing background, and it carries a name that captures something of the wonder it inspires. The pillars of creation rise like great towers of gas and dust in the heart of a nebula called the Eagle, located roughly 7,000 light-years from Earth. When the Hubble Space Telescope captured its famous image of these pillars in 1995, the photograph became one of the most recognized space images in history. The pillars appear against a golden-green glow of background gas, their edges ragged and intricate, shaped by forces that have been working on them for millions of years. Each pillar stretches several light-years from base to tip, dwarfing our entire solar system many times over in sheer physical scale. The name Pillars of Creation was given because these columns are active sites of star formation, places where new stars are slowly being born within the dense interiors. The phrase captures something of the wonder astronomers felt when the details of these structures first became visible with such clarity and beauty. Inside each pillar, hidden from ordinary light, pockets of gas are gradually collapsing under their own gravity, growing denser and warmer over timescales measured in millions of years. Eventually, Some of these pockets will ignite as new stars adding their light to the surrounding nebula and the broader galaxy that contains them. The Eagle Nebula itself, also known by its catalogue name Messier 16, is a much larger structure within which the pillars are merely the most photogenic feature. The full nebula spans roughly 70 light-years and contains numerous other regions of star formation beyond the famous pillars visible in the Hubble image. Hot young stars scattered throughout the nebula produce intense ultraviolet radiation that slowly erodes the pillars from the outside, sculpting their distinctive shapes over vast periods. This process of erosion is gentle but relentless, and the pillars will eventually fade away entirely, though not for hundreds of thousands of years yet. The edges of the pillars are particularly interesting, showing small bumps and protrusions that astronomers sometimes call evaporating gaseous globules, or eggs for short. These are dense knots of material that resist the erosion slightly better than the surrounding gas, creating the intricate, almost finger-like structures visible along the pillar edges. Some of these globules may contain protostars in the very earliest stages of formation, still gathering mass from the surrounding cloud before eventually emerging into visibility. The whole scene is one of slow transformation, destruction, and creation happening simultaneously on timescales, almost impossible for humans to truly comprehend. When the James Webb Space Telescope turned its infrared instruments toward the pillars of creation in 2022, it revealed an entirely different view of this familiar structure. Infrared light passes through dust that would block visible light, allowing Webb to see what Hubble could only hint at in its famous photograph. The new images showed the pillars as more translucent structures, with dozens of young stars visible within and around them, glowing in wavelengths invisible to human eyes. Some of these stars appeared as bright red points, still wrapped in cocoons of dust, their light only now reaching us after traveling 7,000 years. The contrast between the Hubble and Webb images of the pillars offers a gentle lesson in how different kinds of light reveal different aspects of the same object. In visible light, the pillars appear solid and opaque, dark against the glowing background, with sharp-edged shadows and dramatic contrasts that make them so visually striking. In infrared, the same pillars become ghostly and semi-transparent, revealing the activity hidden within their dusty interiors, the young stars otherwise invisible to us. Both views are true, both are real, and together they give us a more complete picture of what these structures actually are and contain. The stars visible in the Webb images are quite young by astronomical standards, most only a few 100,000 years old at most. They are still in the process of forming, still gathering material from the surrounding gas, still settling into the stable state that will define them for billions of years. Some of them shoot out jets of material from their poles, creating thin streams of gas that extend far beyond the pillars themselves into surrounding space. These jets are a common feature of young stellar objects, a sign that the star is still actively accreting material and has not yet reached its final configuration. The pillars themselves are made primarily of molecular hydrogen, the same simple two-atom molecule that makes up much of the gas in the Orion Nebula and other stellar nurseries. Mixed with the hydrogen are traces of other elements, including helium, carbon, oxygen, and small amounts of heavier materials that add to the dusty character of the clouds. The dust grains are tiny, often smaller than the width of a human hair, yet they are crucial in blocking visible light and creating the dark silhouettes we see. Without this dust, the nebulae would appear very different, perhaps less dramatic, certainly less mysterious in their visual character and appearance. The light that Hubble and Webb captured from the pillars of creation left those structures roughly 7,000 years ago, which means we are seeing them as they were. During those 7 millennia, the light traveled through the vast emptiness of interstellar space, eventually reaching our solar system and the orbiting telescopes that finally gathered it. What the pillars look like right now, at this very moment, we cannot know for certain, though astronomers believe they probably look very similar. Changes in such structures happen slowly, over hundreds of thousands of years, so 7,000 years of difference is unlikely to be noticeable. There is something almost meditative about looking at images of the pillars of creation, knowing that this light has been traveling toward us for so long. The photons that struck the telescope's sensors began their journey when humans were just beginning to develop writing, when the pyramids were relatively new. They traveled through space that was mostly empty, past stars and through the voids between them, eventually arriving at precisely the right moment to be captured and shared. The universe delivers its messages slowly, but it delivers them with remarkable consistency across distances and timescales that humble any human achievement. The Eagle Nebula, like the Orion Nebula, is only one of thousands of stellar nurseries scattered throughout the Milky Way, each with its own character. Some are smaller and quieter, producing only a handful of new stars over millions of years in relative cosmic solitude and obscurity. Others are far larger and more active, containing enough material to birth entire clusters of stars that will remain loosely bound to each other. The pillars of creation happen to be among the most photogenic of these structures. But they are not unique, not even particularly rare in the grand scheme. What makes them special to us is partly circumstance and partly the power of that first Hubble image to capture human imagination and wonder. Before 1995, most people had never seen such detailed images of star-forming regions, had never imagined that space contained such sculptural beauty. The pillars of creation became an ambassador for the hidden aesthetics of the universe, a reminder that reality often exceeds our imagination in unexpected ways. They showed us that the cosmos is not merely vast and empty, but full of intricate structures, shaped by simple forces acting over immense timescales. The erosion that sculpts the pillars comes primarily from the radiation of nearby hot stars, particularly a cluster of young giants just outside the frame of the famous image. These stars pour out ultraviolet light and stellar winds, streams of charged particles that gradually strip away the outer layers of the gas columns over many millennia. In a sense, the stars that formed earlier in the nebula are now destroying the very structures that might birth future stars, a kind of cosmic competition for resources. Yet, even as the pillars erode, new protostars are forming within them, racing against the slow destruction to complete their formation in time. This interplay between creation and erosion gives stellar nurseries a dynamic quality, even though the changes happen far too slowly for any human to notice directly. The pillars we see today are somewhat smaller than they were 1 million years ago, and they will be smaller still 1 million years from now. Eventually, the hot young stars will win their slow battle, and the pillars will fade into wisps and then into nothing, their material dispersed back into space, but by then, the stars born within them will have emerged into the galaxy, carrying the legacy of those columns into the future. Beyond the Eagle Nebula and the Orion Nebula, even larger stellar nurseries await our attention in the depths of the galaxy and in space beyond. One of these nurseries dwarfs them all in size and activity, stretching across hundreds of light years and containing some of the most massive stars known. This great cloud of gas and dust glows in the southern skies, too far south for many northern observers to see, but captured in stunning detail by modern telescopes. It is here that we find the Orion Nebula, a place of vast scale and quiet, ongoing creation that seems almost overwhelming in its scope. The Orion Nebula stretches across more than 300 light-years of space, making it one of the largest and brightest star-forming regions visible from Earth. Located roughly 7,500 light-years away in the southern constellation of Carina, it glows with such intensity that it is visible to the naked eye despite its distance. Within this enormous cloud, thousands of stars are in various stages of formation, from dense cold cores just beginning to collapse to fully fledged giants already burning bright. The nebula contains more raw material than Orion and the Eagle Nebula combined, enough to build countless future stars over millions of years. For observers in the southern hemisphere, Carina is one of the true wonders of the night sky, a glowing region that rewards even casual observation. Through binoculars or a small telescope, it reveals layers of complexity. Bright knots and dark lanes of dust winding through the glowing gas in intricate patterns. The nebula has been known to astronomers since the 1700s, though its full extent and nature only became clear with modern instruments and techniques. Today it serves as one of the primary laboratories for understanding how massive stars form and influence their surroundings through radiation. Within the Carina Nebula sits one of the most remarkable stars ever discovered, a giant known as Eta Carinae, or Eta Cara for short. This star is one of the most massive and luminous in our entire galaxy, shining with the light of roughly 5 million suns combined into one object. It has a turbulent history, having undergone a major eruption in the 1840s that briefly made it the second brightest star in the night sky. Today, Eta Carinae is surrounded by twin lobes of gas, called the Homunculus Nebula, material ejected during that eruption and now expanding slowly outward into space around it. Despite its dramatic nature, Eta Carinae sits quietly within the larger nebula, one bright point among many in a vast landscape of glowing gas and dust. The star's light helps illuminate portions of the surrounding nebula, adding to the complex play of light and shadow that gives Carina its distinctive appearance. Astronomers study Eta Carinae carefully, as it represents an extreme example of stellar behavior, a star living fast and burning through its fuel at a tremendous rate. Such massive stars live only a few million years compared to the billions of years expected for smaller stars like our Sun. When the James Webb Space Telescope captured images of the Carina Nebula shortly after beginning its scientific operations, the results captivated audiences worldwide with their beauty. One particular image, showing a structure nicknamed the Cosmic Cliffs, became immediately iconic for its combination of scale and delicate detail throughout the frame. The cliffs are actually the edge of a giant cavity within the nebula, carved out by radiation from young stars just beyond the visible boundary. They rise in a wall of gas and dust that stretches roughly 7 light-years from top to bottom, yet appears in the image like a landscape almost touchable. The cosmic cliffs image reveals hundreds of previously unseen young stars, many still embedded in the gas from which they are forming even now. Some appear as tiny points of light peeking through the dust, while others show the characteristic diffraction spikes of Webb's mirror catching their brilliant radiation. The detail in the image is remarkable, showing structures smaller than our solar system within a scene spanning light-years of actual physical distance. Every wisp and tendril of gas visible in the image is real, shaped by radiation and gravity into forms that will last for thousands of years. The colors in the Webb images of Carina are assigned to represent different wavelengths of infrared light, translated into visible hues for human eyes to appreciate. The blue regions correspond to hot gas energized by nearby stars, while the orange and brown tones represent cooler dust and molecular gas. This color translation is not a fabrication, but a necessary interpretation, allowing us to see what would otherwise remain invisible to our biological senses entirely. The underlying reality is genuine. The structures are there, and the processes are ongoing, regardless of how we choose to represent them visually. Within the Carina Nebula, star formation proceeds at a pace much faster than in smaller nebulae like Orion. Though faster is still measured in hundreds of thousands of years. The massive stars forming here will burn through their hydrogen fuel relatively quickly, living perhaps 10 million years before reaching the ends of their lives. In cosmic terms, these are the mayflies of the stellar world. Brilliant but brief, their influence outsized compared to their actual lifespans within the universe. Smaller stars forming alongside them in the same nursery will outlive them by billions of years, still shining long after the giants are gone. The nebula's immense size means that different regions are in different stages of evolution, creating a living textbook of star formation within a single structure. Some areas are still dark and cold, not yet disturbed by gravitational collapse or nearby stellar radiation, patiently waiting for their time to come. Others are actively forming stars right now, with protostars visible in infrared light, jets streaming from young stellar objects, and pillars of gas slowly evaporating. Still other regions have already completed their star-forming activity, now populated by young clusters of stars that have emerged from their birth clouds. The Carina Nebula belongs to a larger structure called the Carina Sagittarius Arm, one of the spiral arms of our Milky Way galaxy where star formation is concentrated. Along this arm and along the other spiral arms, nebulae like Carina are scattered like beads on a string, each one a site of stellar creation. The spaces between the arms are quieter, with less gas and dust, and correspondingly less star formation happening in those relatively empty regions of the galaxy. This pattern of concentrated activity along spiral arms is common in spiral galaxies throughout the universe, a natural consequence of how galaxies rotate. Looking at the Carina Nebula, even in photographs, conveys a sense of scale that can be hard to fully absorb or comprehend with everyday intuition. The structures we see are so large that light takes years to cross them, yet they appear in images as delicate and detailed as clouds in an earthly sky. This disconnect between apparent fragility and actual immensity is one of the recurring themes of astronomical observation and the wonder it provides. The universe presents itself as something almost graspable, almost intimate, even when the reality involves distances and sizes beyond any human experience. The light from the Orion Nebula that reaches Earth tonight began its journey roughly 70 to 500 years ago, when human civilization was still young. The pyramids of Egypt were under construction, writing was being developed in Mesopotamia, and the first cities were taking shape in river valleys around the world. All of human recorded history has unfolded in the time that light took to travel from Orion to our eyes and instruments, observing the southern sky. And yet, in terms of the nebula's own lifespan, this interval is barely noticeable, a brief moment in an existence spanning millions of years of creation. The dust within Carina, like the dust in all stellar nurseries, plays a crucial role in the star formation process, beyond just creating beautiful visual effects. Dust grains provide surfaces where hydrogen atoms can meet and bond into molecular hydrogen, the form necessary for gravitational collapse to proceed efficiently. Without dust, the gas would remain too warm and too diffuse to form stars in any reasonable time frame, even by cosmic standards of patience. The same dust that obscures our view of young stars is also essential for their formation, a quiet partnership between light and shadow. The colors visible in the nebula, whether in visible light images or infrared translations, arise from specific physical processes happening within the gas itself. When ultraviolet light from hot stars strikes hydrogen atoms, it ionizes them, stripping away their electrons temporarily in an energetic reaction. As the electrons recombine with protons, they emit light at specific wavelengths, creating the characteristic reddish-pink glow of ionized hydrogen seen throughout Carina.
Other elements, like oxygen and sulfur, contribute additional colors when similarly energized, adding to the palette of the nebula.
This process of ionization and recombination is happening continuously throughout the Orion Nebula, powered by the relentless output of the young massive stars within. The energy flows outward from these stellar sources, interacts with the surrounding gas, and is re-emitted as the light that eventually reaches our telescopes. In a sense, the nebula is a vast energy conversion system, transforming the ultraviolet radiation of young stars into the softer, visible, and infrared light we can observe. The beauty we perceive is a byproduct of physics, nature expressing itself through the fundamental rules that govern matter and energy. As we consider the Orion Nebula and its neighbors, a gentle pattern begins to emerge in how stellar nurseries are distributed and what they have in common. They tend to be found in the denser regions of galaxies, where gas and dust accumulate along spiral arms, or in other areas of gravitational concentration. They share common features like dark dust lanes, glowing ionized gas, and populations of young stars in various stages of formation within their structures. And they all operate on timescales so long that human observation captures only frozen moments in processes that span millions of years continuously. The Orion Nebula, the Eagle Nebula with its famous pillars, and the nearby Orion Nebula are all part of this larger family of stellar nurseries scattered throughout our galaxy. Each has its own character and scale, but all are engaged in the same slow work of building new stars from the raw materials left over from earlier cosmic generations. Beyond these well-known examples lie thousands of other nebulae, some spectacular and some modest, each contributing to the ongoing renewal of the stellar population of the Milky Way galaxy. Exploring even a few of these other nurseries reveals the diversity and creativity of the universe in its patient work of stellar creation. The Horsehead Nebula rises like a dark silhouette against a curtain of glowing hydrogen in the constellation Orion. Not far from the more famous nebula we began with, its shape, resembling the head and neck of a chess knight, is so distinctive that it has become one of the most recognizable objects in all of astronomical photography. The Horsehead itself is a dense cloud of dust and gas that blocks the light from the emission nebula behind it, creating its famous profile. This simple arrangement of opaque dust against bright background gas produces an image of startling beauty and quiet mystery. The Horsehead is located roughly 1,500 light-years from Earth, making it a relatively close neighbor in galactic terms, though still immensely far by human standards. It is part of the larger Orion molecular cloud complex, the same vast structure that contains the Orion Nebula we explored at the beginning of our journey. The glowing red backdrop against which the Horsehead appears is known as IC 434, a region of ionized hydrogen energized by nearby massive stars. The bright star Sigma Orionis, visible just to the lower left of the Horsehead in many images, provides much of the illumination that makes the contrast possible. Like the pillars of creation, the Horsehead Nebula is being slowly eroded by the radiation from surrounding hot stars, which gradually strips away material from its surface. The distinctive shape we see today is temporary on cosmic timescales, destined to change and eventually disappear over the next few million years of slow erosion. 5 million years from now, the Horsehead will be unrecognizable, its current form dissolved back into the surrounding space as dust and gas. Yet, even as it fades, new dense regions elsewhere in the cloud may create new silhouettes, new shapes emerging from the ongoing interplay of creation and destruction. The interior of the Horsehead contains material dense enough to potentially form new stars, though it is relatively quiet compared to more active regions, like Carina or Orion. Infrared observations have revealed some small protostars forming within the dusty cloud, their light visible only in wavelengths that can penetrate the obscuring dust. These young stellar objects are still in their earliest stages, perhaps a few 100,000 years old, still gathering mass from their surroundings slowly. Whether any of them will emerge as fully fledged stars before the Horsehead erodes away is uncertain. A quiet race between formation and destruction. Moving deeper into the galaxy, we encounter the Lagoon Nebula, another beautiful stellar nursery lying roughly 5,000 light-years from Earth in the direction of Sagittarius. The lagoon is one of the few nebulae bright enough to be visible to the naked eye under good conditions, appearing as a faint, fuzzy patch in the summer Milky Way. Through telescopes, it reveals a complex structure of bright and dark regions, with a prominent dark lane running through its center that gives it its watery name. The nebula spans roughly 100 light-years across and contains several young star clusters actively forming within its glowing embrace. The central region of the lagoon contains a particularly dense area of star formation, known as the Hourglass Nebula, named for its distinctive double-lobed shape within images. This hourglass structure is created by the radiation and winds from a young massive star at its center, which has blown a cavity in the surrounding gas. The star responsible is called Herschel 36, named after the astronomer who first catalogued it. And it is only about 1 million years old. Despite its youth, Herschel 36 is already shaping its environment dramatically, demonstrating the powerful influence young massive stars can have on the nebulae that birth them. The Lagoon Nebula has been observed for centuries, first noted as a nebulous patch by early telescopic observers, long before its true nature was understood. Giovanni Hodierna observed it in the 1600s, and Charles Messier included it in his famous catalogue of nebulous objects as Messier 8 in 1764. Today, advanced telescopes reveal details those early observers could never have imagined, from individual young stars to the delicate filaments of gas that wind through the nebula. Yet the basic sense of wonder they felt, looking at that faint glow in the summer sky, remains accessible to anyone with a clear night and patience. Further along in our gentle tour, we find the Rosette Nebula, a circular formation of gas and dust that resembles its namesake flower when seen from the appropriate angle. Located roughly 5,200 light-years from Earth in the constellation Nurseries, the rosette spans about 130 light-years in diameter, a significant structure by any measure. At its center sits a young star cluster called NGC 2244, whose hot young stars have blown a cavity in the surrounding gas and illuminate it. The flower-like shape arises from this central clearing and the glowing petals of gas that surround it, a cosmic blossom of remarkable beauty and scale. The stars of NGC 2244 are only a few million years old, making them relative newcomers to the galaxy, despite their appearance as established points of light. Their intense radiation ionizes the surrounding hydrogen gas, causing it to glow with the characteristic reddish-pink color visible in photographs of the rosette structure. The same radiation is gradually pushing the remaining gas outward, expanding the central cavity and slowly dispersing the nebula over millions of years. In perhaps 10 to 20 million years, the rosette will have largely dissipated, its gas spread too thin to maintain its current glowing visibility. These nebulae, the Horsehead and Lagoon and Rosette, represent only a small sampling of the stellar nurseries visible from Earth, with modest equipment. Hundreds more are scattered throughout the Milky Way, each with its own shape and character, each engaged in the slow work of stellar creation over immense timescales. Some, like the Trifid Nebula with its distinctive three-lobed structure, show the interplay of emission, reflection, and dark nebulae, all within a single object. Others, like the vast Tarantula Nebula in the nearby Large Magellanic Cloud, dwarf even the Carina Nebula in size and activity, birthing stars at rates almost unprecedented. The Tarantula Nebula, also known as 30 Doradus, lies in a small galaxy that orbits our own Milky Way, visible from the southern hemisphere as a faint smudge. Despite being roughly 160,000 light-years away, far beyond any nebula within our own galaxy, the tarantula is so bright and energetic that it rivals closer structures. If the tarantula were located at the same distance as the Orion Nebula, it would cast visible shadows on Earth, so intense is its luminous output. It represents star formation at its most vigorous, producing massive stars in quantities that seem almost excessive by the quiet standards of the Milky Way. Each of these nebulae, despite their differences in size and activity level, shares common features that reveal the underlying physics of star formation at work. All contain vast quantities of molecular hydrogen, the basic fuel for stellar creation, mixed with traces of heavier elements and dust particles throughout their volumes. All are shaped by the interplay of gravity, pulling material inward, and radiation pushing outward from already formed stars within their boundaries. And all operate on timescales measured in millions of years, far beyond any human experience yet accessible to our understanding, through careful observation and patient study. The variety of shapes and sizes among stellar nurseries reflects the diversity of conditions in which they form and evolve throughout the galaxy. Some, like the Horsehead, are dense, compact structures destined to produce only a handful of stars before erosion claims them entirely. Others, like Carina, are vast complexes capable of birthing thousands of stars over their extended lifespans of active stellar formation. The particular outcome depends on factors like the density of the original gas cloud, the presence of nearby massive stars, and the local environment within the galaxy itself. Nature produces diversity, even in such fundamental processes as star formation, expressing its creativity across countless variations on a theme. Understanding that the galaxy contains thousands of these nurseries shifts our perspective on the night sky and what it represents to observers on Earth. Every star we see, including our own sun, was born in such a cloud of gas and dust, emerging into visibility after millions of years of gradual formation. The elements that make up our planet and our bodies passed through previous generations of stars, and the nebulae that birthed them in cycles of cosmic recycling. We are, in a very real sense, connected to these distant glowing clouds through the material history of the universe and the patient work it continues. The slow tour through these beautiful structures naturally raises a gentle question about what is actually happening inside them to create new stars. We have seen the shapes and colors, the pillars and cavities, the dark dust lanes and glowing gas, but the underlying process remains somewhat mysterious. How does a vast, diffuse cloud of gas transform itself into the brilliant pinpoints of light we call stars, shining steadily for billions of years? The answer lies in the patient work of gravity, the simplest of forces, acting over timescales that humble any human conception of waiting. Inside every stellar nursery, something quiet is happening that cannot be seen directly with any telescope, no matter how powerful or sensitive its instruments. Deep within the clouds of gas and dust, far from the glowing surfaces visible in photographs, gravity is slowly gathering material together, atom by atom. This process is so gradual that millions of years pass between the first faint stirrings and the eventual emergence of a new star into visibility. Yet despite its slowness, this is how every star in the universe began, including the one that lights our own days on this small planet. Gravity is perhaps the most familiar of all physical forces, the same attraction that keeps us grounded on Earth and holds the moon in its orbit. It is also the weakest of the fundamental forces, easily overcome by other interactions at small scales, which is why we can lift objects despite Earth pulling on them. But gravity has one crucial advantage over stronger forces, which is that it is always attractive and it acts over unlimited distances throughout space. Given enough mass and enough time, gravity will always win, slowly pulling scattered material together into denser and denser concentrations over millions of years. In a nebula, the gas is not uniformly distributed, but contains regions of slightly higher and lower density scattered throughout its vast volume. These density variations might be caused by supernova shockwaves, by stellar winds, or simply by random turbulence within the cloud over its long history. A region that happens to be slightly denser than its surroundings has slightly more gravitational pull, attracting nearby gas toward it at an imperceptible pace. As more gas accumulates, the gravitational pull increases, attracting still more material in a gentle feedback loop that slowly builds momentum over immense timescales. This process of gravitational accumulation is called collapse, though the word suggests something far more sudden and dramatic than what actually occurs in nature. A collapsing gas cloud might take 1 million years to shrink noticeably, with material drifting inward at speeds slower than a human walking pace measured across cosmic distances. There are no sudden implosions, no rapid contractions, just the patient inward drift of countless atoms and molecules, responding to gravity's gentle, persistent invitation. The cloud has nowhere to hurry to, and the universe provides all the time it needs to complete this transformation. As the gas accumulates and the density increases, something interesting begins to happen. At the center of the collapsing region over the millennia, the material pressing inward creates pressure, and this pressure generates heat, gradually warming the core of the forming object above its initial cold temperature. What began as gas, colder than any freezer on Earth, slowly becomes warm, then warmer still as the collapse continues and pressure builds in the center. This heating is a natural consequence of compression, the same principle that makes a bicycle pump warm when you compress air rapidly. The forming object at this stage is called a protostar, meaning a star that is not yet truly a star, but is on its way to becoming one. A protostar does not yet shine by nuclear fusion, the process that powers mature stars like our Sun through the conversion of hydrogen into helium. Instead, it glows from the heat of its ongoing contraction. The gravitational energy being converted into thermal radiation as material falls inward, continuously. This protostellar phase can last for hundreds of thousands of years, depending on the mass of the forming star and the conditions of its environment. During this early phase, the protostar remains hidden within its natal cocoon of gas and dust, invisible to telescopes that observe in ordinary visible light. Only infrared telescopes, capable of seeing through the dust, can detect these young objects, revealing them as warm, glowing points within the cold, dark clouds. The James Webb Space Telescope has proven particularly adept at finding protostars, its infrared instruments piercing the dusty veils that hide them from other observatories. Hundreds of previously unknown protostars have been discovered this way, each one a star in the making, still gathering the mass it will need for future existence. The dust that surrounds a protostar eventually settles into a flattened disk shape, rotating around the young object like a cosmic vinyl record of immense proportions. This disk contains the raw material from which planets might one day form, the same process that created Earth and its siblings roughly 4.5 billion years ago. The protostar continues to accrete material from this disk, growing larger and more massive as time passes in its slow journey towards stellar ignition. Some of the material in the disk may also fall inward in spiraling streams, feeding the hungry protostar at its center continuously. Many protostars also produce jets, narrow streams of material shooting outward from their poles at high speeds in opposite directions from each other. These jets are thought to carry away excess angular momentum, allowing the protostar to continue accreting material without spinning itself apart from the rotation. The jets can extend for light years, punching through the surrounding cloud and creating structures visible in telescope images of active star-forming regions. They are one of the signatures astronomers look for when searching for young stellar objects within nebulae, indicators of ongoing formation. As the protostar continues to contract and heat up over hundreds of thousands of years, the temperature at its core gradually rises toward a crucial threshold. When the core temperature reaches roughly 10 million degrees, something remarkable happens that marks the true birth of a star in the nuclear sense. At this temperature, hydrogen atoms are moving fast enough and are packed closely enough that they can begin to fuse together, combining to form helium. This fusion reaction releases energy, the same process that powers the sun and will power it for billions of years to come. The onset of fusion is not an explosion or a sudden ignition, but a gradual transition as conditions at the core become suitable for sustained nuclear reactions. Once fusion begins, the energy released creates an outward pressure that balances the inward pull of gravity, stabilizing the star against further contraction. This balance between gravity and pressure will define the star for most of its lifetime. A delicate equilibrium maintained continuously for billions of years. The protostar has become a true star, a self-sustaining nuclear furnace that will shine steadily until its fuel is eventually exhausted. The time required for a star to form, from initial gravitational collapse to the onset of fusion, depends strongly on the mass of the forming object. A massive star, many times heavier than our Sun, might complete its formation in only a few 100,000 years due to its stronger gravity pulling material inward more quickly. A star like our Sun takes longer, perhaps 50 million years from first collapse, to stable hydrogen burning in its core. The smallest stars, barely massive enough to sustain fusion at all, might take over 100 million years to complete their formation, patience defining their very existence. Once fusion begins, the new star quickly becomes the dominant influence on its immediate surroundings, even though it may still be embedded in its parent cloud. The radiation pouring from its surface begins to heat and ionize the nearby gas, creating a small glowing region around the young star within the larger nebula. Stellar winds, streams of particles flowing outward from the star's surface, push against the surrounding material, gradually clearing a cavity around the newborn object. This process of clearing can take millions of years, during which the star remains partially hidden, its full brilliance not yet visible to distant observers. Eventually, the star emerges from its dusty cocoon, its light finally able to shine unimpeded into the surrounding space and beyond to observers on distant worlds. This emergence marks the end of the formation process and the beginning of the star's main sequence lifetime, the long, stable period that defines most stellar existence. For a star like our Sun, this stable phase will last roughly 10 billion years, an almost unimaginably long time of steady, reliable shining before changes begin. The newborn star joins its siblings in the cluster where they formed, each one a success story of gravity's patient work, The newly visible stars illuminate the gas around them, contributing to the glowing appearance of the nebula that gave them birth in the first place. They also begin to shape that nebula through their radiation and winds, carving cavities, eroding pillars, and dispersing the remaining gas over time. In this way, the very stars created by the nebula eventually destroy it, spreading its material back into space to seed future generations of star formation. The process is cyclical, a slow rhythm of creation and dispersal that has been repeating throughout the galaxy for billions of years now. In the Orion Nebula, the trapezium stars we mentioned at the beginning of our journey are examples of this newly emerged generation of stellar objects. They have only recently become visible, their light now dominating the central region of the nebula and illuminating the gas for light years around them. Thousands of other young stars in Orion are still hidden within the cloud, still gathering mass, not yet ready to emerge into full visibility for human observers. In a few million years, many of them will have completed their formation, adding their light to the cosmic glow we can already see tonight. This slow process of stellar creation is happening right now in nebulae across our galaxy. Thousands of new stars gradually taking shape within clouds of gas and dust. Most of these forming stars will never be observed by any human telescope, too distant or too obscured or too faint to attract our limited attention. Yet they form regardless, the universe conducting its patient work without any need for acknowledgement or appreciation from beings like ourselves, observing from afar. The stars that will shine billions of years from now are already beginning their journeys, though they will not complete them for ages yet. The moment a new star begins to shine marks a transition from hidden potential to visible presence within its host nebula and the galaxy beyond. That first light, generated by nuclear fusion at the core, must travel outward through the star's outer layers before finally escaping into surrounding space. The journey from core to surface takes thousands of years, the light being absorbed and re-emitted countless times as it works through the dense stellar material. Only then does it begin its far longer journey across interstellar space, traveling until it encounters something, perhaps a telescope, perhaps an eye, perhaps nothing at all. For a young star still embedded in its parent nebula, the first challenge is simply escaping the dusty cocoon that has surrounded it since formation began millions of years before. Dust grains absorb visible light efficiently, converting it to infrared radiation, which is why young stellar objects are often invisible in ordinary photographs, but bright in infrared images. As the star's radiation and winds gradually clear the surrounding material, more visible light escapes, and the star becomes progressively brighter to distant observers over thousands of years. This gradual emergence is like a slow sunrise, the star revealing itself incrementally as the obscuring dust disperses. The color of a new star's light depends primarily on its surface temperature, which is determined by the star's mass and the rate at which it generates energy. Massive stars are hotter and bluer, their surfaces reaching temperatures of tens of thousands of degrees Kelvin, radiating intense ultraviolet light along with visible blue wavelengths. Smaller stars are cooler and redder, their surfaces at perhaps 3,000 to 4,000 degrees, glowing with a warm orange or red light that seems almost gentle. Our Sun, a medium-sized star, shines with a yellow-white light, corresponding to its surface temperature of roughly 5,700 degrees Kelvin. The most massive young stars have a particularly dramatic effect on their surroundings due to their intense ultraviolet radiation output, affecting nearby gas. When this energetic light strikes hydrogen atoms in the surrounding nebula, it ionizes them, stripping away their electrons and creating a region of hot, ionized gas. These regions, called H2 regions in astronomical terminology, glow with the characteristic reddish-pink light of hydrogen recombination we have seen throughout our journey. The Orion Nebula, the Eagle Nebula, the Carina Nebula, and all the other glowing stellar nurseries are essentially H2 regions illuminated by their young, massive stars. The size of an H2 region depends on the power of the central star and the density of the surrounding gas that absorbs its radiation. A single hot, massive star can ionize a bubble of gas light years across, creating a glowing cavity within the larger cold molecular cloud. Multiple massive stars together, like the trapezium in Orion, can ionize even larger volumes, their combined radiation clearing vast regions of space around the central cluster. These ionized regions are where most of the visible beauty of stellar nurseries comes from. The interaction of stellar light with surrounding gas, creating the colors we admire. Beyond simply ionizing the gas, young massive stars also drive powerful stellar winds, streams of particles flowing outward from their surfaces at hundreds of kilometers per second. These winds carry mass away from the star, slowly eroding it over time. But more importantly, they push against the surrounding nebula material continuously. The wind creates a bubble of hot, low-density gas around the star, bounded by a shell of compressed material where the wind meets the ambient cloud. Over time, these wind-blown bubbles can merge together, creating complex structures within the nebula shaped by the combined influence of multiple stars. The pillars of creation that we explored earlier are examples of structures shaped by these stellar winds and radiation from nearby massive stars outside the visible frame. The pillars are essentially shadows, dense regions that have resisted erosion better than the surrounding less dense material that has been stripped away entirely. Their distinctive shapes arise from this differential erosion, the denser cores standing tall while the softer material around them has been blown away over millennia. Given enough time, even these pillars will succumb, their material dispersed into space by the relentless energy of the young stellar population nearby. Young stars often form in clusters, groups of dozens to thousands of stars born from the same parent cloud at roughly the same time, in cosmic terms. The trapezium in Orion, the cluster at the heart of the Rosette Nebula, and the massive cluster in Carina are all examples of this clustered birth pattern. Stars in a cluster share a common origin, formed from the same molecular cloud, having similar ages and similar initial chemical compositions, despite individual variations. Over time, the cluster may remain bound together by gravity, or it may gradually disperse, the member stars drifting apart into the general galactic population. The Sun is thought to have formed in such a cluster roughly 4.5 billion years ago, along with perhaps a few thousand other stars. Those stellar siblings have long since scattered across the galaxy, dispersed by gravitational interactions and the differential rotation of the Milky Way over billions of years. Today, we have no way of identifying which stars in the sky might have shared the Sun's birthplace, though astronomers have searched for chemical signatures that might reveal them. The cluster that birthed our solar system has dissolved completely. Its members now spread across thousands of light-years of galactic space. The transition from protostar to main sequence star is not the end of stellar evolution, but merely the beginning of a long, stable phase that defines most stellar lifetimes. A star like our Sun will spend roughly 90% of its total existence as a main sequence star, steadily burning hydrogen in its core and maintaining a constant luminosity. During this long period, the star serves as a stable source of light and heat for any planets that might orbit it, providing the consistent conditions life requires. The Sun has been in this phase for about 4.5 billion years and will continue for roughly another 5 billion before changes begin. Massive stars, despite their greater fuel reserves, burn through their hydrogen much faster than smaller stars due to the higher temperatures at their cores. A star 50 times the mass of the Sun might have a main sequence lifetime of only a few million years, barely a cosmic instant compared to smaller stars. These brief stellar lives mean that massive stars are always relatively young, their presence in a nebula indicating recent star formation in that region within the past few million years. The trapezium stars, Eta Carinae, and the massive stars illuminating the pillars of creation are all examples of this bright but brief stellar category. The jets that many young stars produce during their formation phase gradually fade as the star completes its accretion and settles into stable hydrogen burning. The disk of material around the star also evolves, some of it falling onto the star, some being blown away by stellar winds, and some potentially forming planets over millions of years. By the time a star fully emerges from its parent nebula, it may already be accompanied by a retinue of young planets, moons, and smaller bodies. Our own solar system likely completed its basic planetary architecture within the first 100 million years after the Sun's formation, a relatively quick process by cosmic standards. As young stars clear their immediate surroundings and disperse the remaining gas, the nebula that gave them birth gradually fades and dissipates over millions of years. The glowing regions become dimmer as less gas remains to be ionized. The dark pillars erode and vanish, and the once distinct cloud spreads into the general interstellar medium. Eventually, only the stars remain, shining in a cluster or scattered across space, the only permanent legacy of the nebula that formed them eons ago. The nebula itself was always temporary, a stage of cosmic evolution rather than a permanent structure, beautiful but transient on galactic timescales. The colors of these nebulae, which have accompanied us throughout this journey, arise from specific physical processes that reveal the composition and conditions of the glowing gas. Understanding where these colors come from adds another layer of appreciation for the beauty we observe, connecting visual aesthetics to underlying physical principles at work. The universe paints with a limited palette, but the results are endlessly varied. The same basic colors appearing in nebulae across the cosmos, yet always arranged differently. The soft pinks and deep reds that dominate many nebula images arise primarily from hydrogen, the simplest and most abundant element in the universe, and the raw material for stars. When ultraviolet light from hot young stars strikes hydrogen atoms in the surrounding gas, it ionizes them, temporarily stripping away their electrons completely. The free electrons eventually recombine with protons to form neutral hydrogen again, releasing light in the process as they settle back into stable configurations. The most prominent of these emission lines occurs at a wavelength of 656.3 nanometers, a deep reddish-pink color known as hydrogen alpha emission. This hydrogen alpha light is responsible for the dominant color in nebulae, like Orion, the Lagoon, the Rosette, and countless other H2 regions scattered throughout the galaxy. It is the signature color of ionized hydrogen, appearing wherever young hot stars illuminate the surrounding gas with their ultraviolet radiation throughout the visible universe. The consistency of this color across different nebulae reflects the universal nature of atomic physics, hydrogen behaving the same way everywhere, regardless of location in space. A hydrogen atom in the Orion Nebula emits the exact same wavelength of light as one in the Carina Nebula or in any distant galaxy billions of light years away. Other elements contribute additional colors to the nebula palette, each with its own characteristic emission wavelengths determined by atomic structure. Oxygen, the third most abundant element in the universe after hydrogen and helium, produces distinctive blue-green emission lines when ionized by stellar radiation. One particularly prominent oxygen line occurs at 507 nanometers, contributing teal and green hues to nebula images where oxygen is abundant. The combination of hydrogen alpha red and oxygen green creates the varied color schemes visible in many nebula photographs taken through specialized astronomical filters. Sulfur also contributes to nebula colors, emitting light at wavelengths in the red portion of the spectrum, slightly different from hydrogen alpha emission. When astronomers create composite images using different filters, they often assign distinct colors to hydrogen, oxygen, and sulfur to reveal the distribution of elements. The famous Hubble palette, used in many iconic nebula images, assigns red to sulfur, green to hydrogen, and blue to oxygen, creating striking false color images. These color assignments do not represent what human eyes would see directly, but reveal real information about chemical composition and physical conditions within the nebulae. Beyond emission, nebulae also exhibit reflection, where dust grains scatter light from nearby stars, rather than emitting their own light from atomic transitions. Reflection nebulae typically appear blue, just as Earth's sky appears blue for similar physical reasons, involving the scattering of light by small particles. The dust grains in nebulae scatter shorter blue wavelengths more efficiently than longer red wavelengths, creating blue halos around some stars, embedded in dusty regions. The contrast between blue reflection regions and red emission regions adds visual complexity to many nebulae. Different physical processes operating in different areas. The Trifid Nebula provides a particularly clear example of this contrast, showing emission, reflection, and dark nebulae all within a single structure visible in telescope images. The emission regions glow reddish pink with ionized hydrogen. The reflection regions appear blue where scattered starlight dominates, and dark dust lanes divide the nebula into thirds. This combination of three distinct nebula types in one object inspired its name, from the Latin word for divided into three parts. The Trifid demonstrates how multiple physical processes can operate simultaneously within a single region of space, creating visual complexity from simple underlying causes. Dark nebulae, like the horsehead we explored earlier, represent regions where dust is dense enough to block light from behind, completely without any foreground illumination. These regions appear as silhouettes against brighter backgrounds, their shapes defined by absence rather than presence of light reaching our telescopes. The dust grains responsible for this absorption are typically made of carbon compounds and silicates, similar in some ways to soot and sand, but formed in the outer atmospheres of dying stars, without any stars embedded within them or nearby to illuminate them. These clouds remain dark and cold, invisible except as shadows against brighter regions. The colors captured by ground-based telescopes and space observatories undergo various processing steps before being released to the public as finished images. Raw telescope data is often captured through narrowband filters that isolate specific emission wavelengths rather than the broadband filters that mimic human color vision. Astronomers combine multiple filter images to create composites, assigning colors that may or may not match human perception of the original wavelengths captured. The resulting images are scientifically accurate in the sense that they represent real differences in emission, even if the specific color assignments are somewhat arbitrary. This processing does not mean the images are false or fabricated, only that they represent translations from data into visual form that humans can appreciate. The structures, shapes, and relative brightness distributions in processed nebula images are all real, corresponding to actual physical features of the objects being observed. An astronomer studying such an image gains real information about element distribution, temperature variations, and ionization conditions within the nebula. The beauty we perceive is a fortunate side effect, the universe happening to produce structures that appeal to human aesthetic sensibilities when rendered appropriately. Infrared images, like those from the James Webb Space Telescope, require even more dramatic translation, since infrared light is completely invisible to human eyes under any circumstances. Webb captures light at wavelengths ranging from roughly 0.6 to 28 micrometers, far beyond the roughly 0.4 to 0.7 micrometers visible to humans. To create images we can see and appreciate, different infrared wavelengths are assigned to visible colors, typically blue for shorter wavelengths and red for longer. The resulting images show us a universe that would otherwise remain completely hidden, revealing structures and objects invisible to optical telescopes. The translation of invisible light into visible images connects to a broader truth about astronomical observation and the nature of cosmic beauty itself. Much of what makes nebulae beautiful to us is the result of choices made by image processors, the color assignments and contrast adjustments that render raw data into art. Yet the underlying reality is genuine. The gas is there, the stars are there, the structures are there, regardless of how we choose to represent them. The universe provides the canvas and the shapes, and we provide the palette that makes them visible to our limited human senses. Perhaps the most remarkable aspect of nebula colors is how they connect to the deeper story of cosmic chemistry and element formation over billions of years. The hydrogen glowing pink in Emission Nebulae was created in the first few minutes after the Big Bang, the original primordial element of the universe. The oxygen contributing blue-green hues was synthesized inside previous generations of stars, fused from lighter elements and released into space when those stars died. The dust grains creating dark silhouettes were formed in the outer atmospheres of red giant stars, carbon and silicon, combining into complex molecules as the stars aged. Every color we see in a nebula represents a chapter of cosmic history, elements created at different times and places throughout the 13.8 billion year story of the universe. The hydrogen is almost as old as time itself, while the heavier elements are products of stellar processing, recycled through multiple generations of stars. The new stars forming within these nebulae will incorporate all of these elements, mixing primordial hydrogen with stellar processed metals to create objects of varied composition. And someday, some of those new stars will die and return their material to space, enriching future nebulae with even heavier elements for further generations. This cosmic recycling connects every nebula we have visited, Orion and the Pillars and Carina and all the rest, into a single ongoing story of matter transforming through time. The gas that forms stars today was once inside previous stars, and before that, it drifted through space as part of earlier nebulae, stretching back to the earliest epochs. Nothing in the universe is truly new, only recombined and transformed, the same atoms participating in endless cycles of stellar birth and death across billions of years. The colors we admire in nebula images are visible traces of this deep history, encoded in the wavelengths of light emitted by ancient elements. The material that glows within stellar nurseries did not appear from nothing, but accumulated over billions of years through the patient work of earlier stellar generations. Every atom of oxygen, carbon, nitrogen, and other heavy elements in a nebula was once inside a star, synthesized through nuclear fusion, and released when that star reached the end of its long life and returned its enriched gases back into the surrounding space. This process of stellar recycling has been occurring throughout our galaxy for over 13 billion years, quietly building up the chemical complexity we observe today. The nebulae we have been exploring are not merely birthplaces, but also repositories of ancient stellar material, gathered and waiting to become something new. When a star like our Sun approaches the end of its life, it does not simply fade away but undergoes a gentle transformation over millions of years. The outer layers of the star gradually expand and cool, puffing outward like breath on a cold morning, drifting slowly into the surrounding space. This process creates what astronomers call a planetary nebula, though the name is somewhat misleading since planets have nothing to do with it. Early observers saw these round, glowing shells and thought they resembled the disks of distant planets, and the name simply remained. The Ring Nebula in the constellation Lyra offers one of the most beautiful examples of this gentle stellar ending, visible from Earth. At its center sits a small, hot remnant of the original star, now compressed into a dense white dwarf, no larger than our planet. Surrounding this fading core, a shell of glowing gas expands outward at roughly 15 miles per second, carrying with it elements forged over billions of years. The blues and greens near the center come from oxygen, while the outer red regions glow with the light of hydrogen and nitrogen. Another famous example is the Helix Nebula, sometimes called the Eye of God because of its striking circular appearance in photographs. This structure lies about 700 light-years from Earth and spans roughly 2 light-years across, making it one of the closest planetary nebulae to our solar system. The gases flowing outward from the central star will eventually disperse into the surrounding interstellar medium, mixing with existing clouds of hydrogen and helium. Over millions of years, this enriched material may find its way into a stellar nursery, becoming part of the next generation of stars. The distinction between these ending nebulae and the birth nebulae we explored earlier is worth holding gently in mind as you rest. Planetary nebulae represent the final exhalations of sun-like stars, while emission nebulae like Orion and Carina are active nurseries where new stars form. Yet both are part of the same vast cycle, connected across timescales that dwarf human comprehension. The oxygen glowing in the Ring Nebula may one day become part of a planet orbiting a star not yet born. Larger stars contribute to this cosmic recycling in more dramatic ways, though even their endings unfold over timescales that feel slow by human standards. When a star significantly more massive than our Sun exhausts its nuclear fuel, the core collapses rapidly, while the outer layers are expelled in a supernova. These powerful events scatter heavy elements across vast distances, seeding the surrounding space with iron, gold, and other materials too heavy to form in smaller stars. The Crab Nebula in Taurus represents the remnant of such an event, recorded by Chinese astronomers nearly 1,000 years ago. Yet even supernova, for all their power, are merely accelerated versions of the same recycling process that quieter stars accomplish over longer periods. The essential pattern remains the same across all stellar masses and lifetimes. Stars gather material from nebulae, transform it through fusion over millions or billions of years, and eventually return enriched gases to the interstellar medium. This returned material mixes with existing clouds, gradually increasing the proportion of heavy elements available for the next generation of star formation. The carbon atoms in every living thing on Earth were forged inside stars that died before our solar system existed. The oxygen we breathe, the nitrogen in our atmosphere, the calcium in our bones, all trace their origins to stellar interiors and the nebulae that gathered their ashes. This connection between our physical bodies and ancient stellar processes is not poetic interpretation, but straightforward chemistry, verified through spectroscopy and nuclear physics. We are quite literally made of recycled stardust, gathered into temporary forms before eventually returning to the cosmic cycle. This realization carries a certain quiet comfort that requires no exaggeration or spiritual language to appreciate. The atoms that compose you have been part of the universe for billions of years and will continue existing for billions more after your current form disperses. Nothing is truly created or destroyed in these processes, only transformed and recombined in endlessly varying patterns. The stellar nurseries we have been exploring are simply the current chapter in a story that began with the first stars and continues tonight. The enrichment of the interstellar medium happens gradually, generation by generation, like interest compounding over cosmic timescales. The earliest stars in the universe formed from nearly pure hydrogen and helium, with almost no heavier elements present in the primordial gas. These ancient stars lived their lives, scattered their processed materials, and contributed to clouds that would form the next stellar generation. Each successive generation incorporated slightly more heavy elements than the one before, slowly building the chemical diversity we observe today. Our Sun is considered a population 1 star, meaning it formed relatively recently from gas already enriched by many previous generations. The proportion of heavy elements in the Sun, though small compared to hydrogen and helium, is significant enough to allow rocky planets like Earth to form. Older population II stars, found in the galactic halo and globular clusters, contain far fewer heavy elements because they formed from less processed material. The very first stars, called Population 3, have never been directly observed, but likely contained essentially no heavy elements at all. This generational pattern means that the nebulae we observe today are chemically different from those that existed 8 or 10 billion years ago. The Orion Nebula contains more oxygen, carbon, and nitrogen than a similar structure would have held in the early universe. Future stellar nurseries will be even more enriched, as the current generation of stars eventually contributes its processed materials to the interstellar medium. The chemical evolution of our galaxy is a slow but measurable process, recorded in the composition of stars at different ages. Planetary nebulae, like the Ring and the Helix, will fade over tens of thousands of years as their gases disperse and cool beyond visibility. The white dwarf stars at their centers will continue cooling for billions of years, gradually dimming until they become cold, dark remnants called black dwarfs. No black dwarfs exist yet, because the universe is not old enough for any white dwarf to have cooled completely. This is another reminder of the timescales involved in these processes. Timescales that make human history seem like the briefest instant. The gases released by planetary nebulae travel outward at modest speeds, eventually merging with the general interstellar medium over periods of hundreds of thousands of years. There they join hydrogen flowing in from intergalactic space, material ejected by other dying stars, and debris from ancient supernovae. This mixture slowly accumulates in the spiral arms of the galaxy, where gravitational compression can eventually trigger new episodes of star formation. The journey from one stellar generation to the next may take hundreds of millions of years, but it proceeds steadily. Some of the material in the Orion Nebula may have passed through this cycle multiple times, having been part of 3 or 4 stellar generations before arriving in its current location. Each passage through a stellar interior added new elements to the mix, transforming simple hydrogen into the rich chemical soup we observe today. The colors that make nebulae so beautiful in photographs are direct evidence of this enrichment, each wavelength corresponding to specific atoms present in the gas. Without this cosmic recycling, the universe would contain only hydrogen, helium, and trace amounts of lithium. The idea that stellar nurseries are simultaneously endpoints and beginnings gives them a quality that transcends simple categorization. They are places where old material becomes new stars, where the past is transformed into the future, where continuity takes physical form. This is not mysticism, but observation, the kind of slow realization that emerges from centuries of patient astronomical work. The cycle of stellar birth, life, death, and rebirth is perhaps the most fundamental rhythm of the visible universe. As you rest and allow these ideas to settle, you might find a certain peace in knowing that this process requires no intervention or maintenance to continue. Stars form, burn, and die according to physical laws that operate the same way everywhere in the cosmos. The recycling of stellar material happens automatically, driven by gravity and nuclear physics, requiring nothing but time and the vast spaces between stars. The universe is its own gardener, tending to the growth of new stars from the remains of the old. The connection between stellar nurseries across the galaxy becomes clearer when we consider this recycling on larger scales. Material ejected from a dying star in one region may eventually drift toward a nebula thousands of light years away, contributing its atoms to star formation in a completely different part of the galaxy. These slow migrations occur over tens of millions of years, invisible to any single observer, but measurable through careful study. The Milky Way functions as a single vast ecosystem, with matter flowing continuously between birth regions and death sites. This perspective naturally draws our attention outward, from individual nebulae to the galaxy that contains them all, a structure so large that light takes 100,000 years to cross it. The Milky Way stretches across roughly 100,000 light years, a flattened disk of stars, gas, and dust rotating slowly around a central bulge that harbors an enormous black hole. Within this vast structure, stellar nurseries are not randomly distributed, but concentrated along the spiral arms where gas density is highest. These arms are not solid structures, but rather density waves, regions where material bunches together temporarily before dispersing and reforming elsewhere. As gas enters these denser regions, gravitational compression can trigger the collapse that eventually produces new stars. Our solar system currently resides in a minor spiral arm called the Orion Arm, or sometimes the Orion Spur, located between two larger arms called Perseus and Sagittarius. The Orion Nebula lies within this same arm, which is why it appears relatively nearby at just over 1,000 light-years distance. Other famous nebulae occupy different arms entirely, their light traveling much farther to reach our telescopes and our eyes. The Orion Nebula, for instance, lies in the Sagittarius arm, roughly 70 to 500 light-years from Earth. If you could view the Milky Way from above, looking down on its spiral pattern, the stellar nurseries would appear as bright knots along the curving arms. These concentrations of star formation give the arms their distinctive appearance, making them more luminous than the regions between them. The spaces between the arms are not empty, but simply contain less dense gas, making star formation less common in those regions. Stars born in the arms eventually drift away as the galaxy rotates, populating the disk with older stellar generations. The rotation of our galaxy is remarkably slow when measured against human timescales, requiring approximately 230 million years for the Sun to complete a single orbit around the galactic center. This period is sometimes called a cosmic year or a galactic year, a useful measure for considering events that span multiple rotations. Dinosaurs roamed the Earth about 1 galactic year ago, while the first complex life appeared roughly 2 galactic years in the past. The Sun has completed approximately 20 orbits since its formation 4.5 billion years ago. During each galactic orbit, the Sun passes through different environments, sometimes moving closer to the denser regions of spiral arms, and sometimes drifting through quieter inter-arm spaces. The effects of these passages on Earth are subjects of ongoing research, with some scientists proposing connections to mass extinction events or climate variations. However, these ideas remain speculative, and the dominant influence on Earth's conditions comes from much closer sources, like solar activity and volcanic eruptions. The galaxy's structure affects us only subtly, if at all. Star formation rates across the Milky Way have varied over the galaxy's long history, with periods of more intense activity followed by quieter intervals. Currently, our galaxy produces roughly 1 to 3 new stars per year, a modest rate compared to some more active galaxies in the universe. This gentle pace means that most regions of the galaxy are quiet most of the time, with star formation occurring in scattered locations rather than everywhere simultaneously. The nebulae we have been exploring represent the small percentage of galactic volume where new stars are actively forming. The total number of stars in the Milky Way is estimated at somewhere between 100 billion and 400 billion, a range that reflects the difficulty of counting objects we cannot directly observe. Many stars are hidden behind dust clouds, located in crowded central regions, or simply too dim to detect with current instruments. The true count may never be known precisely, but even the lower estimates represent a number larger than most human minds can meaningfully grasp. Each of these stars formed in a nebula drew material from the interstellar medium and will eventually return that material when it dies. Among these hundreds of billions of stars, many host planetary systems, similar in some ways to our own solar system. The discovery of thousands of exoplanets over the past 3 decades has revealed that planets are common throughout the galaxy, not rare exceptions. Some of these planets orbit within stellar nurseries, bathed in the light of nearby young stars and surrounded by the gas and dust of their natal clouds. Others have long since left their birthplaces, carried by their parent stars into quieter regions of the galactic disk. The Milky Way is not alone in space, but accompanied by several dozen smaller satellite galaxies, gravitationally bound to our own. The largest of these are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light separate from the main band of the Milky Way. Both Magellanic Clouds contain active stellar nurseries, including the Tarantula Nebula in the Large Magellanic Cloud, one of the most vigorous star-forming regions in our entire galactic neighborhood. This nebula alone contains enough gas to produce millions of new stars over the coming millions of years. Beyond our immediate neighborhood, the Andromeda Galaxy represents the nearest large spiral galaxy, located roughly 2.5 million light-years from Earth. Andromeda contains its own population of stellar nurseries, visible in detailed images as pink and red patches along its spiral arms. The light reaching us from Andromeda tonight left that galaxy when early humans were first developing stone tools, a reminder of the vast distances separating even nearby galaxies. Yet Andromeda and the Milky Way are slowly approaching each other, destined to merge in approximately 4 to 5 billion years. This future merger will dramatically reshape both galaxies, triggering intense bursts of star formation as gas clouds collide and compress throughout the combined structure. New nebulae will form in regions that are currently quiet, while existing nurseries may be disrupted or enhanced by the gravitational turmoil. The night sky seen from any surviving planets would look utterly different during and after the merger, filled with unfamiliar star patterns and new constellations. Yet, even this cosmic collision will unfold so slowly that no human lifetime could perceive the changes directly. For now, the Milky Way continues its steady, patient rhythm of star formation without external disruption. Gas flows inward from satellite galaxies and the intergalactic medium, replenishing the raw material consumed by stellar nurseries. Old stars shed their outer layers, enriching the interstellar medium with heavier elements. New stars form in the spiral arms, live out their varied lifespans, and eventually contribute their processed materials to future generations. This cycle has continued for over 13 billion years and shows no signs of ending. The galaxy we inhabit is neither exceptionally active nor unusually quiet when compared to similar spiral galaxies throughout the observable universe. It forms stars at a moderate rate, contains a typical amount of gas and dust, and displays a fairly ordinary spiral structure. This ordinariness is perhaps reassuring, suggesting that the processes we have been exploring are common throughout the cosmos. Stellar nurseries like Orion and Carina have countless counterparts in other galaxies, each quietly producing new stars according to the same physical principles. Looking at the Milky Way as a whole helps contextualize the individual nebulae we have visited during this journey. The Orion Nebula, so prominent in our winter sky, represents just one small patch of activity in an arm containing thousands of similar regions. The pillars of creation, famous though they are, constitute a tiny fraction of the Eagle Nebula, which itself occupies only a small portion of the Sagittarius arm. The Carina Nebula, vast by local standards, appears as merely a bright spot when the entire galaxy is considered. This progression of scales can feel dizzying, but it can also bring a sense of quiet perspective. The interstellar medium between these active regions is not truly empty, but filled with extremely diffuse gas and dust spread across light years of space. This material is so thin that the best laboratory vacuums on Earth contain far more particles per cubic centimeter than typical interstellar space. Yet over sufficient volumes, even this sparse material adds up to tremendous masses, providing the raw material that will eventually fuel future episodes of star formation. The galaxy is patient, gathering material over millions of years before anything dramatic occurs. As we allow our perspective to expand from individual nebulae to the galaxy and beyond, the pace of cosmic processes becomes even more apparent. Nothing in the Milky Way is rushing toward any particular destination or deadline. Stars form when conditions allow, burn for as long as their fuel lasts, and return their materials when their time is complete. The galaxy rotates, the spiral arms wind slowly across the disk, and the cycle continues without urgency or interruption. This patient rhythm has characterized the universe since the first galaxies formed, and it will continue for billions of years to come. The timescales involved in star formation and stellar evolution extend so far beyond human experience that they require a deliberate shift in thinking to appreciate. A single star may take 10 million years to form, from initial gravitational collapse to the ignition of nuclear fusion in its core. This duration is roughly 5,000 times longer than modern humans have existed as a species, longer than the entire evolutionary history of our genus. Yet in cosmic terms, 10 million years is a relatively brief period, a small fraction of a star's eventual lifespan. Once a star like our Sun begins fusing hydrogen in its core, it can continue doing so for approximately 10 billion years before exhausting its fuel. Our Sun is currently about halfway through this main sequence phase, having burned steadily for 4.5 billion years, with roughly the same duration still remaining. Throughout this immense span, the Sun's output has remained remarkably stable, varying by less than a fraction of a percent over millions of years. This stability has allowed life on Earth to develop and persist without interruption from our parent star. Smaller stars burn even longer, their modest masses requiring less energy output to balance against gravitational collapse. Red dwarf stars, the most common type in the galaxy, can continue fusing hydrogen for trillions of years, far longer than the current age of the universe. No red dwarf has yet died of old age, because the universe is simply too young for any of them to have exhausted their fuel. The oldest red dwarfs, formed shortly after the first galaxies appeared, still have more than 90% of their hydrogen remaining. Larger stars, by contrast, burn through their fuel with surprising speed, despite having more material to consume. A star 10 times the mass of the Sun may exhaust its hydrogen in only 10 or 20 million years, barely long enough to count as middle-aged by red dwarf standards. These massive stars shine with tremendous brilliance during their brief lives, illuminating the nebulae around them before ending in spectacular supernova. The brightest stars we see in the night sky are often these short-lived giants, visible across great distances despite their relative rarity. The Orion Nebula contains stars spanning this full range of masses and expected lifespans, from red dwarfs that will burn for trillions of years to blue giants that may survive only a few million. The trapezium stars at the nebula's center fall toward the higher end of this scale, destined to exhaust their fuel within the next several million years. When these stars reach the end of their lives, they will significantly alter the surrounding nebula through their death throes. But that alteration lies so far in the future that thousands of human civilizations could rise and fall before it occurs. The nebulae themselves will change over these vast timescales, though the changes will be imperceptible to any single generation of observers. The pillars of creation, those famous columns of gas and dust, are being slowly eroded by radiation from nearby stars. Astronomers estimate that the pillars may be completely dissipated within the next million years or so, leaving behind only the stars that formed within them. Yet, a million years from now, no human eyes may remain to notice this transformation. And the process itself is so gradual that no single photograph could capture it. This slowness can feel frustrating to a species accustomed to measuring time in years and decades rather than millions and billions. We want to see the changes, to witness the formation of a star or the sculpting of a pillar. But the universe operates on its own schedule, indifferent to our desire for visible progress. The comfort in this indifference is that nothing requires our attention or intervention to continue. The stars will form whether we watch or not, and the nebulae will evolve without our guidance or approval. The light we observe from distant nebulae provides a peculiar window into this cosmic slowness, showing us not the present, but the past. Light from the Orion Nebula left that region approximately 1,300 years ago, during the early medieval period on Earth. Light from the Carina Nebula departed 7,500 years ago, when humans were first developing agriculture and permanent settlements. Light from more distant nebulae in other galaxies may have traveled for millions or billions of years before reaching our telescopes. This temporal displacement means that we are always observing the past, never the present, when we look at the night sky. The stars we see may have changed significantly or even ceased to exist during the time their light was traveling toward us. For nearby objects, this delay is negligible, but for distant galaxies, we are seeing conditions that prevailed when Earth was young or even before our planet existed. The universe becomes a kind of time machine, allowing us to observe earlier epochs simply by looking farther away. Yet despite this temporal complexity, the processes we observe remain fundamentally the same across all these distances and time periods. Stars formed billions of years ago in distant galaxies through the same gravitational collapse and nuclear fusion that produces stars in the Orion Nebula today. The physics has not changed, and the cosmic cycles have continued without interruption since the first stellar generations appeared. This consistency is one of the great discoveries of modern astronomy. The realization that the universe follows the same rules everywhere and at all times. The patience required to understand these processes mirrors in some ways the patience required to observe them. Astronomers spend entire careers studying phenomena that will not significantly change during their lifetimes. They measure tiny variations, track slow motions, and build models that predict behavior across millions of years. This scientific patience mirrors the cosmic patience that characterizes the phenomena themselves. Understanding the universe requires accepting that some questions cannot be answered quickly, and some changes cannot be witnessed directly. For a listener resting comfortably, this cosmic patience can serve as a gentle reminder that not everything requires immediate attention or resolution. The nebulae we have explored will continue their slow transformations regardless of human schedules or concerns. Stars will form, burn, and die, whether we understand the process or not. The universe has been conducting these operations for billions of years without human participation, and will continue for billions more after our species has passed. There is a certain freedom in contemplating processes that neither need nor request our involvement. The changes that do occur within human timescales are usually too subtle to notice without careful measurement and comparison. Astronomers comparing photographs taken decades apart can sometimes detect small motions or brightness variations in nebulae and stellar objects. The expansion of the Crab Nebula, for instance, has been measured over the past century, confirming its origin in the supernova of 1054 AD. But these measurable changes represent the exception rather than the rule, visible only because of the relative youth and violence of the Crab Nebula's formation. Most stellar nurseries appear essentially frozen in time when viewed across human lifespans, their structures unchanged from photograph to photograph. The pillars of creation look the same today as they did when the Hubble Space Telescope first imaged them in 1995, and they will look the same when future telescopes observe them decades hence. This apparent stillness conceals the incredibly slow motions occurring within, motions that will completely transform these structures over geological timescales. The universe reveals its changes only to those patient enough to wait. This contemplation of deep time naturally leads to consideration of how our understanding of these celestial objects has developed over the centuries of human observation. Humans have been looking at the night sky for as long as our species has existed, but our understanding of what we were seeing has evolved dramatically over millennia. The earliest observers saw points of light, bands of brightness, and occasional fuzzy patches without any framework for understanding their true nature. They created stories and patterns to make sense of what they saw, connecting stars into constellations and attributing significance to planetary motions. These early interpretations were creative and meaningful within their cultural contexts, even if they bore little resemblance to physical reality. The fuzzy patches visible to the naked eye presented particular challenges to early observers trying to categorize celestial objects. The Orion Nebula, visible as a smudge below the three belt stars, was noted by various cultures, but rarely distinguished clearly from the surrounding stars. The term nebula, derived from the Latin word for cloud or mist, was eventually applied to these indistinct objects to acknowledge their different appearance. But what nebulae actually were remained mysterious for centuries after they received their name. The invention of the telescope in the early 17th century transformed astronomical observation, revealing structures invisible to the unaided eye. Galileo turned his telescope toward the Milky Way and discovered it was composed of countless individual stars too faint and close together to resolve separately. Other observers examined the fuzzy patches and found that some resolved into star clusters, while others remained cloudy regardless of magnification. This distinction would eventually prove significant, separating what we now call open clusters from true nebulae. Charles Messier, a French astronomer in the 18th century, compiled a famous catalogue of fuzzy objects, specifically to help comet hunters avoid confusion. His list of 110 Messier objects includes many of the nebulae and star clusters visible from the northern hemisphere, numbered in roughly the order he encountered them. The Orion Nebula became M42 in this catalogue, the Crab Nebula M1, and the Ring Nebula M27. These designations remain in common use today, a reminder of the catalogue's enduring usefulness to amateur and professional astronomers alike. The nature of nebulae remained contentious well into the 20th century, with different observers proposing radically different explanations for their fuzzy appearance. Some astronomers believed all nebulae were distant collections of stars that would resolve under sufficient magnification. Others argued that some nebulae were genuinely gaseous, composed of diffuse material rather than individual stellar points. The debate was eventually settled through spectroscopy, the analysis of light broken into its component wavelengths. When astronomers examined the spectrum of the Orion Nebula, they found bright emission lines characteristic of glowing gas, rather than the continuous spectrum typical of starlight. This discovery confirmed that at least some nebulae were genuinely gaseous, composed of atoms energized by nearby stars and emitting light at specific wavelengths. The identification of hydrogen, oxygen, and other elements in nebula spectra provided the first direct evidence of chemical composition in objects beyond our solar system. Spectroscopy transformed astronomy from a purely observational science into a tool for understanding cosmic chemistry. The early 20th century brought further advances that clarified the distinction between different types of fuzzy objects observed in the night sky. Some nebulae, particularly the spiral-shaped ones, proved to be entirely separate galaxies, lying millions of light-years beyond the Milky Way. Edwin Hubble's observations in the 1920s established this extragalactic nature conclusively, expanding the known universe. Other nebulae, like Orion and the Pillars of Creation, were confirmed as objects within our own galaxy, clouds of gas and dust illuminated by local stars. Photography revolutionized the study of nebulae by capturing details invisible to observers peering through eyepieces in real time. Long-exposure photographs accumulated light over minutes or hours, revealing faint structures that no human eye could perceive directly. The famous photographs of nebulae that circulated in popular publications during the 20th century were products of this accumulated exposure, showing colors and details impossible to see through a telescope in a single moment. These images brought the beauty of stellar nurseries to audiences who had never looked through a telescope themselves. The launch of the Hubble Space Telescope in 1990 marked another transformation in our ability to observe nebulae and other celestial objects. Positioned above Earth's atmosphere, Hubble could capture images with clarity impossible from ground-based observatories. The 1995 photograph of the Pillars of Creation became one of the most recognizable astronomical images ever taken, appearing in textbooks, posters, and countless popular presentations. This single image did more to popularize stellar nurseries than decades of earlier observations had accomplished. Hubble continued operating for decades beyond its planned lifespan, producing thousands of images that revealed the structure of nebulae in unprecedented detail. The telescope observed star-forming regions across the Milky Way and in nearby galaxies, building a comprehensive picture of how stellar nurseries function. Astronomers used these observations to refine their models of star formation, identifying the stages through which protostars pass before igniting as full-fledged fusion reactors. The theoretical understanding and observational evidence advanced together, each informing the other. The James Webb Space Telescope, launched in late 2021, represented the next major step in our ability to study stellar nurseries and other cosmic phenomena. Webb operates primarily in infrared wavelengths, detecting light that can pass through the dust clouds, obscuring visible light observations. This infrared vision allows Webb to peer inside nebulae, revealing protostars and young stellar objects hidden from Hubble's optical cameras. The telescope's first public images included a stunning view of the Orion Nebula's cosmic cliffs, showing structures invisible in previous observations. Webb's observations of the Pillars of Creation provided a dramatic demonstration of the telescope's capabilities, revealing stars embedded within the dusty columns that appeared opaque in Hubble's images. These hidden protostars had been suspected based on infrared observations from earlier instruments, but Webb provided the clearest confirmation yet of their existence. The comparison between Hubble's visible light images and Webb's infrared views illustrated how different wavelengths reveal different aspects of the same cosmic structures. Both perspectives are valuable, together providing a more complete picture than either alone. The progression from naked eye observation to Messier's catalogue to spectroscopy to space telescopes represents centuries of accumulated human effort and ingenuity. Each generation of astronomers built upon the work of their predecessors, adding new observations and new interpretive frameworks to the growing body of knowledge. This slow accumulation of understanding mirrors in some ways the slow accumulation of stellar material in nebulae themselves. Both processes require patience and the contributions of many participants across long stretches of time. Modern astronomers studying stellar nurseries benefit from this accumulated heritage, building on centuries of observations and theoretical developments. They use sophisticated computer models to simulate the collapse of gas clouds and the formation of protostars, comparing their predictions against observational data. They combine observations across multiple wavelengths, from radio waves to X-rays, to understand different aspects of the star formation process. They collaborate across institutions and national boundaries, sharing data and interpretations in ways that accelerate the pace of discovery. Yet despite all these advances, much about stellar nurseries remains uncertain or unknown, waiting for future observations and theoretical insights. The precise mechanisms that trigger gravitational collapse in some regions while leaving others stable, the factors determining whether a collapsing cloud produces a single massive star or a cluster of smaller ones, are not fully understood. The role of magnetic fields in shaping nebula structure and directing gas flows continues to be investigated. Science progresses by recognizing what it does not yet know. The history of observing stellar nurseries is ultimately a story of human curiosity, sustained across generations, each building on the achievements of those who came before. The fuzzy patches that puzzled ancient observers have become detailed, three-dimensional maps of cosmic gas and dust. The mysterious glow that defied explanation for centuries is now understood as emission from specific atomic species excited by stellar radiation. The seemingly static structures in photographs are now known to be sites of slow but steady transformation, creating new stars from ancient materials. This accumulated knowledge belongs to everyone, not just the astronomers who compiled it through painstaking observation and analysis. Anyone looking at the Orion Nebula tonight sees the same object that Galileo examined through his primitive telescope 4 centuries ago. The understanding has changed dramatically, but the object itself continues its slow evolution regardless of human attention. The nebula neither knows nor cares that we have learned to decipher its structure and composition, yet somehow this feels like cause for quiet celebration. As our journey through stellar nurseries approaches its conclusion, we might simply rest with the recognition that these processes continue tonight, as they have for billions of years. Somewhere in the Orion Nebula at this very moment, though we cannot perceive it, a dense core of gas is slowly contracting under its own modest gravity. The atoms within this core are drifting closer together at speeds too slow to measure directly, gradually increasing the density at the center of the clump. Millions of years from now, if the contraction continues uninterrupted, the center of this core will become warm enough and dense enough for hydrogen fusion to begin. A new star will join the hundreds already shining within that vast cloud of gas and dust. This process is occurring simultaneously in stellar nurseries throughout the Milky Way. In the Carina Nebula and the Eagle Nebula, and countless regions too distant or obscured for our telescopes to observe. Gas is collapsing, protostars are warming, and young stars are beginning to shine in places that have no names and may never receive them. The galaxy is quietly busy with star formation, though the pace is so slow and the distance is so vast that the activity passes unnoticed by casual observers. Only patient, systematic study reveals the extent of ongoing stellar birth. The stars being born tonight include some that will still be shining billions of years in the future, long after our sun has exhausted its hydrogen and expanded into a red giant. Small red dwarfs forming in the Orion Nebula may continue burning for trillions of years, outlasting not only our sun, but most of the stars currently visible in the night sky. These modest stars will persist through cosmic eras that have not yet begun, witnessing changes in the galaxy that current astronomy cannot predict. Their patience will far exceed their brilliance. Other stars being born tonight will burn more briefly, but more spectacularly, consuming their fuel in millions rather than trillions of years. These massive stars will illuminate their surroundings with intense radiation, sculpting the nebulae around them before ending their lives in dramatic fashion. The elements they create through fusion will return to the interstellar medium, enriching future stellar nurseries with heavier atoms. Their contribution to cosmic chemistry will outlast their individual existence by billions of years. The Milky Way itself continues its slow rotation, carrying the Sun and Earth around the galactic center at roughly 500,000 miles per hour. This motion is imperceptible to us, masked by the even greater distances to the stars we see in the night sky. We are participants in a cosmic dance whose choreography spans hundreds of millions of years, tracing out spiral arms and passing through different galactic neighborhoods. The stellar nurseries we observe from Earth will eventually be left behind as our solar system drifts along its orbital path. The nebulae we have visited during this journey will change over the coming millions of years in ways we cannot directly observe. The pillars of creation will gradually erode under the radiation pressure from nearby stars, their distinctive columns dissipating into the surrounding space. The Orion Nebula will exhaust its reservoir of star-forming material. The trapezium stars will age and evolve, and eventually the entire region will look quite different from its current appearance. Yet these changes will unfold so slowly that countless human generations could pass without noticing any transformation. This slowness is not a limitation, but a characteristic feature of cosmic processes, as fundamental to the universe as gravity or nuclear fusion. The patience of stellar nurseries reflects the patience of physical law itself, operating steadily across timescales that dwarf human experience. There is no hurry in the formation of a star, no deadline for the enrichment of the interstellar medium, no schedule for the rotation of galaxies. Everything proceeds at its own natural pace, determined by density and temperature and gravity rather than intention or impatience. The universe we inhabit is old beyond easy comprehension, having existed for approximately 13.8 billion years since the initial expansion we call the Big Bang. During this immense span, countless stellar generations have formed, burned, and returned their materials to space. The atoms now gathering in stellar nurseries may have passed through multiple stellar interiors, each passage adding new elements to the cosmic inventory. This recycling has been occurring since the first stars appeared, and it will continue until the last stars fade, billions or trillions of years in the future. Looking up at the night sky from wherever you happen to rest, you see light that departed its sources years or centuries or millennia ago. The Orion Nebula you might observe on a clear winter night shows conditions that prevailed when medieval scholars were debating the nature of the heavens. More distant objects reveal even more ancient light, photons that began their journey before humans existed, before complex life appeared on Earth, sometimes before our planet itself had formed. Every photograph and every observation is a record of the past, preserved across distances too vast for the present to be perceived. Yet this pastness does not diminish the connection between observer and observed, between the consciousness contemplating the cosmos and the cosmos being contemplated. The light may be old, but the experience of seeing it is immediate and present. The wonder evoked by stellar nurseries occurs now, in minds capable of appreciation and curiosity. The universe produces observers who find it remarkable, though whether this is coincidence or something deeper remains beyond scientific determination. We simply find ourselves here, aware and wondering. The stellar nurseries we have explored throughout this journey continue their work regardless of our attention or awareness. Stars are forming tonight in Orion, in Carina, in the Eagle Nebula and the Lagoon and the Rosette and countless other regions scattered through the spiral arms. Gas is collapsing, protostars are warming, young stars are pushing back against the clouds that birthed them. This activity requires no permission and no supervision. only the steady operation of physical law across astronomical distances and timescales. Perhaps there is comfort in contemplating processes so vast and so patient that human concerns fade into proper perspective. The worries that occupy waking hours seem smaller against a backdrop of stellar nurseries producing new suns over millions of years. The urgencies that demand attention become less pressing when viewed from the distance of light years, rather than the proximity of daily life. The universe offers this perspective freely to anyone willing to look up and consider what the darkness contains. The night sky, visible from Earth, represents only the tiniest fraction of the cosmos, a local neighborhood within a galaxy that itself occupies a small portion of the observable universe. Beyond the Milky Way lie billions of other galaxies, each containing billions of stars, many of which formed in nebulae similar to those we have been exploring. The processes we have contemplated are not unique to our galaxy, but common throughout the cosmos, occurring wherever gas and gravity and time combine to produce new stellar generations. And so the journey concludes not with any definitive ending, but simply with a return to quietude and the ongoing rhythm of cosmic creation. The nebulae continue their slow transformations, the stars continue their patient burning, and the galaxy continues its stately rotation through the darkness of intergalactic space. These processes have continued for billions of years and will persist for billions more, requiring nothing from us except perhaps occasional appreciation. The universe simply is, vast and patient and beautiful in its steady operation. The Orion Nebula will be there tomorrow night and next year and 1,000 years from now, slowly producing new stars from ancient gas. The light from Carina will continue arriving at Earth, carrying information about conditions that prevailed millennia ago. The cosmic cycles of birth and death and rebirth will continue their endless repetition as they have since the first stars formed, and as they will until the last stars fade. Within this vast continuity, a moment of rest is not an interruption, but a participation, a small consciousness briefly contemplating the immensity that contains it. The stars that form tonight will shine for billions of years, far longer than any human lifetime or any human civilization. They will outlast our species and our planet, and perhaps our entire solar system, burning steadily until their fuel is finally exhausted. And when they eventually die, their materials will return to the interstellar medium, available for future generations of stars that may form after our sun has faded to a cold remnant. The cycle continues without end, patient and persistent and quietly beautiful. There is nothing more required now, no conclusion to reach or lesson to extract from these contemplations. The nebulae exist, the stars form, and the universe proceeds along its ancient paths. If sleep comes easily while holding these images in mind, that is simply what happens when a tired mind encounters something vast and peaceful. If wakefulness persists for a while longer, that too is acceptable, a brief additional moment of quiet awareness before rest arrives. Either way, the stars continue their work, indifferent to whether they are observed, creating themselves from dust and time and gravity. Good night from the drowsy astronaut. The night stretches on and the universe continues.